This interview is in the InterPore Time Capsule series, where people behind important contributions to porous media tell the background history. And I'm here now with Signe Kjelstrup and Dick Bedeaux, who have done important contributions to irreversible thermodynamics on transport phenomena near and across surfaces and interfaces. They have more recently developed the thermodynamics of confined fluids in nanoporous media based on the Hill approach. Before we get into what these contributions are, let's delve into their respective backgrounds. Signe, we start by your background. So why science, why chemistry, and why irreversible thermodynamics?
As you know, Alex, I was growing up in the north of Norway, and to do that makes a spectacular impression on a child, because nature and everything is so dramatic. The midnight sun, the polar lights, you name it. So I was always interested in nature, and my father fostered that. He had radio lectures on astronomy, and I thought that was fascinating when I looked at the northern lights. And he also encouraged me to study sciences. So he advised me to come to the Norwegian University of Science and Technology. But when I came here, I was about to start in physics. There were no female professors, and there were only a few out of the 1,000 students starting that were women. So in physics, 2, I think. So, and the advisors of my father said she will not get a job. So I started chemistry. But there is such a thing as physical chemistry, where I ended. And then I was only in my second year when there was a big event in campus. And that was on the occasion of the Nobel Prize to Onsager in 1968. And I couldn't enter the lecture, but my coming thesis advisor did, and he was very enthusiastic. So when I eventually found him as a teacher, he said to me, "Let us do something in this field." And then we decided to seek for applications in chemistry.
And I note that your first book, Signe, was Irreversible Thermodynamics Without Tears from 1988. Who did you write it for?
With Irreversible Thermodynamics Without Tears. The tears were then what we hoped to achieve, to avoid with the chemists. So big effort was put into writing the book as clearly as possible, or simple as possible. And my co-author, Katrine Seip Førland, should be mentioned in that respect.
Why is it that irreversible thermodynamics is part of the field of chemistry much more than physics?
Because what is essential in irreversible thermodynamics compared to the simple transport laws we had before, like Fick, Fourier, Ohm, and Darcy, is irreversible thermodynamics introduces coupling, and coupling is much more important in chemistry. You can't have a process across the membrane of an ion without it dragging along water, so you immediately have coupling. And there is also coupling to charge and to chemical reactions, and to describe this, the full matrix is actually needed to describe a battery, lithium battery, like we have just published. So I think that the physicists are not in so much need of this coupling. That's why there is a difference. But when that is said, I really wish that the subject should be taught because it has other aspects. it gives a precise definition of the second law, not as an inequality, but as a precise analytical expression. And that the world is needing in this effort we need to make to have better energy efficiency of processes.
Dick, your background, you originate from the strong Dutch tradition in statistical mechanics.
The tradition, for me, in a sense, was started by Arend Vest, who is scientifically my great-grandfather. My grandfather was then Kramers, and my scientific father is then Nico van Kampen, who is my thesis advisor. He was a person that was extremely clear in his lectures, defining concepts properly, clearly, and so that attracted me, and that made that I ended up being his graduate student. Now, that was not quite as easy as you would like, but I mean, it was difficult to get to talk to him, and in that sense, he was a difficult thesis advisor, but he made me strong because I had to explain things to him very well whenever I then got the opportunity. And by the time I had my thesis kind of nearing the end, he disappeared for a sabbatical to the US of A. And in that time, he clearly never read what I was sending him, because when he came back, he had, according to his notes in what I had sent him, read it until page 14. And then he asked me, is the rest also correct? And I was by that time hard enough to say, of course, otherwise I wouldn't have written it. And then he said, well, you rewrite it a bit and then you should make an appointment for your defense, which I then did.
I remember meeting Nico van Kampen once, and he was clearly quite a character. How was it to work as a graduate student with him?
Yeah, Van Kampen was very clever and in that sense a wonderful thesis advisor. However, he was also difficult. He himself got his degree with Kramers, who got his degree with Arend Vest, who got his degree with Boltzmann. So my scientific heritage is in that sense very much into statistical mechanics. And of course Van Kampen was very good in statistical mechanics. He was a little bit strange in the sense that he would tend to not believe anything that other scientists in the field would do. So he would explain us that the Kubo relations were wrong, and would explain us why the Kubo relations were wrong. And of course that was very stimulating, because I immediately studied the Kubo relations and I thought they were perfectly okay. And so in that sense it taught me to disagree with him. In addition to that, he had of course much against the work of Prigogine. I also studied that, and I fear that there I agreed to a large extent with him. Of course, later, after my thesis, I went to America, but then I came back and I worked with Peter Mazur. And of course, Peter Mazur was a very good friend of Prigogine. He also disagreed with Prigogine on these things, but that was all extremely interesting. But Nico van Kampen was in a sense interesting because he always tried to not see me. So if I kind of asked him, I want to talk to him, he would say, yes, yes, we should talk, and then he would run away. So I taught myself to corner him so that he couldn't run away. And then I would say, when he would say yes, would say, well, what about this afternoon? And then he would kind of say yes again and run away again. But then I had an appointment, and I also caught him in his statements, because he had a very clear tendency to do everything using differential equations. And after his advice trying to do that didn't work, I went other ways, and I used the linear theory of perturbation theory of operators, which is an extremely interesting field, and Van Kampen didn't like it. But I used it to prove what I had to prove, but that was the reason. I think that when I got my thesis kind of ready, he escaped to America for a sabbatical, and when he came back he had read the first 14 pages and said, well, you have to rewrite it, but is the rest also correct? And I said, yes, otherwise I wouldn't have written it. And he said, well, after you have rewritten it, you can make your appointment for a defense. So that was Nico van Kampen.
Yeah. You, Dick, have written a book on light scattering from rough surfaces. Where does that fit into your career?
Well, that was in fact a very important moment, and it related to the observation that in order to describe surfaces you need excess densities. And in that particular case, it was the polarization. You had an excess polarization along the surface and an excess polarization parallel to the surface. And now the excess polarization parallel to the surface causes actually the dielectric constant to have a singularity at the surface, the parallel dielectric constant, and it causes the electric field not to be continuous across the surface. But in the normal direction, actually, there is a polarization normal to the surface, but that finds its origin in the inverse dielectric constant, which has to have a singularity. And that causes the displacement field to be discontinuous at the surface. Well, after all the work I did with Jan Vlieger on this subject, we wrote a book about that subject. But meanwhile, I had also realized that actually the work that Gibbs had been doing, in which he defined excess densities, he had only been doing that for equilibrium systems. And you could extend that, and in addition to having excess densities of variables, you could also have excess fluxes along the surface, and that makes it then possible to develop non-equilibrium thermodynamics for surfaces, where quantities like the normal fluxes normal to the surface, are all of a sudden scalar. They are no longer vectorial, and they can therefore directly couple to the reaction at the surface. And so also a temperature difference across the surface can drive a reaction at the surface. So I started to work with Albano and with Mazur actually on formulating non-equilibrium thermodynamics for surfaces. And that actually drew attention, for instance, of Majid Hassanizadeh, an important person in InterPore. He came to Leiden to discuss exactly this work about non-equilibrium thermodynamics and transport for surfaces, along surfaces and through a surface, in his quest to derive equations on the macro level, the Darcy level, for porous media, starting with the description in the pores. And in the pores, of course, the surface effects are important, and therefore he consulted me. That was a very interesting discussion, but it took then, I fear, another 15 years before you personally got me and Signe to go into doing non-equilibrium thermodynamics for porous media.
Your first common book was on irreversible thermodynamics of heterogeneous systems. Please explain.
Yeah, when we first met and discussed, it was clear that we didn't understand each other. And I came from the chemistry background and he came from the statistical mechanical background. But we did understand that there was something to gain by combining our experiences, because I understood that everything in chemistry happens at interfaces. The catalyst interface, the electrode, the membrane, their interfaces are crucial. And here he was with all this knowledge about how things should be properly written for the interface. So,
well, the reason I wanted to talk to her about this issue was that in order to derive Maxwell's equations for the surface, you have certain problems. Because you have to use the Maxwell equations in vacuum, which are Lorentz invariant. However, the description for the surface is Galilei invariant. Now, that implies that you have to neglect certain things, and I was seeking advice of what would be important or not. Well, it was clear that this question was not a question to put to chemists. But I did listen to her, and it was clear that she understood where she was talking about, and that made me eager to get closer to experimental interpretation of matters at the surface, and then to talk again. And the book is a result.
yes, so the book is an extension of the irreversible thermodynamics for bulk phases, like everybody had been written it after Onsager, and me included. And so that we could deal with the dynamic surface. That is the extension, the combination of the two things, the bulk and the surface. And this is our big contribution, I think, to transporting.
Yeah, the surface can move, and the fluxes on both sides have velocities that are different from the velocity of the surface. And the whole theory has to be done, therefore, not in the barycentric frame of reference, as the grote mesure typically do, but you have to do it in the frame of reference of the surface. And that's an important ingredient in getting Onsager of entropy productions for the surface that make any sense.
So then you have a precise description of the entropy production at the surface, and you also have a dynamic boundary condition. But it's only transport perpendicular to the surface that we have treated. So there is still the transport along, and that is then waiting, of course. Yeah.
Trondheim has an interesting place in the history as far as reversible thermodynamics goes. Can you elaborate on this?
Well, I have a lot of contact with Trondheim because I was appointed to be a professor in theoretical physics in 1981. And the reason that they appointed me was because of my work on statistical mechanics, and in particular on the description of surfaces and also the non-equilibrium thermodynamics of surfaces. And so I went to Trondheim, and there I had a lot of contact with Per Hammer and Eivind Hishauge, who were both very good colleagues in that field, and they were also very much connected to the Netherlands, where they were good friends of Hans van Leeuwen and Mathieu Ernst, and they would visit the Netherlands to visit these people, and Mathieu Ernst and Hans van Leeuwen would also come here in Trondheim, and they would write papers together, and in that sense Trondheim was clearly a center in which statistical mechanics was very actively done.
And Alex, you yourself is a part of that group and tradition, I think. So you are the flag carrier right now.
Thank you. Yeah. Signe, you co-edited the collective works of Lars Onsager. What's his place in history or in this field?
Yeah, the collected works, that was obvious. We celebrated his birthday in '93, and then people said to us, why don't you make his collected works? And of course we should do that. And we have since then collected all his things here. And the aim or the purpose is, of course, to show to the younger generations that we have this ideal role model, I would say, in science, right here. His alma mater. He never got a job in Norway, but he came back every year, and with his stature in the field, that makes even us a bit visible, that he had this connection. Yeah.
Signe, you co-edited the collected works of Lars Onsager. What's his place in the history of this field?
Oh, Onsager has a tremendous important role in many fields, but he got the Nobel Prize for irreversible thermodynamics. Everybody asked what he got it for, but it was for irreversible thermodynamics, and this university is his alma mater. So he didn't get a job in Norway, but he always kept contact and came every year back to Norway. So it was logical for this group of my colleagues in physics and me, physics and mathematics, to celebrate that we had Onsager as an ideal for this school of science. And when we did that, in '93, Onsager's birthday, we were asked, why don't you make the collected works? They were not done yet at that point. And everybody means that that is important because of his contributions to the many fields. And we could do it, and with some confidence, because there has always been a strong group in statistical mechanics in this university, and you are one of them to lift that flag high. So I think altogether I'm happy to have that role model so strongly present for younger generations here now.
Where do you see this field is going? Irreversible thermodynamics is applicable in many settings. You wrote a book which recently came in a second edition, namely Irreversible Thermodynamics for Engineers. Is this something that engineers can use in their daily work?
Well, this is my dream or vision, you could say, that such a book could be the standard textbook for teaching thermodynamics in a modern way in universities world over. And the reason is obvious. Equilibrium thermodynamics has to do with equilibrium and states. And you can compare different states, but non-equilibrium thermodynamics includes the dynamics going from one state to the other. And it computes precisely the entropy production along the way, which you don't compute in another way. And speaking about the need for energy efficient processes and precise models for what is the interaction of phenomena in electrolytes and wherever, I think there is, if we want to improve on what is already there in the industry, this theory is needed. So that is my hope, that we could benefit the world in this way.
You also have several books behind you, the latest one being Nanothermodynamics. Can you say a few words about it?
Yes, nanothermodynamics is an extremely interesting field because it goes into a spectrum of systems that cannot be properly described with thermodynamics. And the reason for that is that they are too small. And one of the reasons we got ourselves entangled in that was that we had this feeling that when we were doing simulations, which is by nature not an infinitely large system, it's always a relatively small system, and the question came up how to use the data there to obtain results for the large system. And well, that didn't work so well until we discovered the book by Hill about the thermodynamics of small systems. And Hill is very clever in the sense that he extends the theory that was developed by, Carnot, Clausius, and Gibbs, by adding an additional term. And that additional term describes the smallness of the system. And it comes in by looking at an ensemble of small systems, and the ensemble of small systems together form a big system. So as a function of the number of small systems, of the number of replicas, the system is again Euler homogeneous of the first order, and you can go through the whole analysis, and then you obtain new equations. And an important quantity that is found is what is called the subdivision potential, because it actually measures the energy that you need to subdivide a given amount of internal energy, entropy, number of particles over a larger subset of replicas. And that, of course, gives you a measure of the energy difference depending on the size of the replicas. And that aspect we have used and expanded on in the book, and we have, contrary to what Hill, I fear, is doing, he tends to say, well, you know, when you control the volume, you need two pressures, not one. And then when he comes to another case where he controls the number of particles, he makes the observation, well, this is exactly the same as when you control the volume and you do not control the number of particles, and then you have to do everything yourself. And that, for an uninitiated person in the field, is not easy. And that is why we wrote the book, and we do it explicitly for 6 ensembles, expanding on Hill and extending Hill also, because we actually bring forward the importance of the subdivision potential, and we just wrote a paper on measuring it. Yeah.
In short, then, the hope is that it could serve as an alternative path to get the continuum equations that we do need for the complicated porous media, and that you also are pioneering an effort to find such a description. So I hope in the end that we will be able to more directly compare and see and learn what the assumptions behind each systematic approach are, and how they can complement each other. So there is a lot to do in the future.
Signe, you have recently published papers with biologists on the structure of the seal nose. Elaborate.
Yes, and that was extremely fun. Yeah, because the seal nose has a very interesting labyrinthic structure. And why is that? It is, we think, because it has a very efficient system for saving heat and body heat and water in the Arctic climate where it lives. And that structure-function relationship is fascinating, and I would really like to explore that in other contexts as well. Because what if nature has invented such structures that are efficient? Shouldn't we then try and copy them in technology? That is a question I could pose to many people, including myself.
Looking back at their long careers, any advice to young scientists?
Yes. The important thing is to be independent, to trust yourself, and to not believe what all the established older people are telling you as the truth about the world.
And I would like to add, follow your heart and find a group where you can enjoy working. A person doesn't have to be many in the group. Could be only you and one more.
Yeah.